Hello, I'm Josh Wood. This is my peer grade assignment for the Managing Machine Learning Projects course in Coursera. The problem that I've chosen is valuation models for both dealers and consumers in Canadian used car market. Currently, there's inadequate predictive modeling methods used for vehicle valuations. And what happens is dealers tend to take advantage of consumers because they don't have access to the right data. But this also causes an issue for dealer-consumer transaction friction, which is also a problem for dealers. Retail consumers do not have access to the right data to make an informed decision. ML can help solve this problem because we could create a valuation output that assesses multiple factors to create that vehicle valuation, which would inevitably take the guesswork out of creating that valuation output. And who cares about this? Well, consumers as well as dealerships do care. Valuation provided by a trusted third-party source would not only provide a peace of mind for the consumer because it's coming from a reputable source, but it also remove friction for the dealers during the sales process without having to argue about the valuation output because it's coming from that trusted source. The business understanding here, the target user would obviously be retail consumers as well as retail remarketers or dealers. Poor vehicle valuation outputs favor either the consumer or the dealer, and this is where that friction comes in. Either the number's too high or the number's too low, and they're not able to land at a fair middle point. Consumers want peace of mind, and dealers want to increase their win ratio, so both of these problems could be solved with a solution. Current valuation models usually just use an average clustered price from a geographic location, a sample taken and then averaged out, and then they'll layer on some basic regression adjustment for odometer readings. It's not very accurate. And they do not consider enough data points, which leads to manual adjustments made by dealers. And they typically end up undervaluing a consumer's vehicle. A good example of this is a damage adjustment. So the business impact, which would define a successful outcome, is creating a model that is proven to be more accurate and closer to an actual sold price. We'd use actual sold records to feed the valuation model. Accurate valuation would lead to increased adoption of our valuation solution, which would in turn increase profitability for our company in other area of our current business. We shoot to reduce the average gap between the prediction and actual sold value. So we'd use mean standard error of the aggregate predictions. And the constraints here would be just a agreeable middle point between dealers and consumers. Inevitably, what happens is a number being too high is good for the consumer and bad for the dealer, and a number that's too low is good for the dealer and bad for the consumer. So landing on a middle ground, which is right in the middle expectation of both, which they could both agree is fair, would be the best possible outcome. Potential factors that we'd use in our model, the vehicle decode elements, year, make, model, trim, engine, drivetrain, transmission, body style, and box length. We'd layer on historical attributes like damage, both damage type and damage amount, number of previous owners, number of service records and previous use type, whether it was a personally owned vehicle, a fleet vehicle, or a rental. We'd factor in a location adjustment, usually inputted with a postal code to get to that regional adjustment. Number of kilometers is very important for an input, and then also seasonality, so time of year. Thinking of a convertible in winter is not as desirable. Likewise, a four-wheel drive in summer is not as necessary as in winter. Our validation plan would be a 90-10 split. We'd use 90% for training and 10% holdout for testing. We could generate about 100,000 observations biweekly. Tried this multiple different ways. We started with multiple linear regression, moved up to random forest, and we ended up landing on a gradient boosted tree as the selected model, as it was the most effective with the data we were putting in. The design system would be cloud, offline learning, and online predictions. we would require an internet connection, and data can be sent to the cloud, which lands us on the cloud versus the edge. The model will get retrained bi-weekly, and retraining this model 10 to 14-day intervals for updates is more than sufficient for the users. So this suggests offline learning, and we do need real-time predictions for customers, and this is be offered through API or on online web service. So online predictions would be used. The potential risks, data drift would be something to be considered, but this can mostly be mitigated by refreshing the model every 10 to 14 days. The refresh cadence should be able to mitigate that risk by updating with fresh data within that time frame. The bigger concern would be concept drift. The markets can experience drastic shifts in buying behavior, and this was really noticeable during the COVID shutdown, where vehicle valuation outputs were very inaccurate 2 weeks after the shutdown, and most models that were currently in market updated every 30 days or every quarter. So those models were very inaccurate at that point. Additional concerns that we'd have to consider and mitigate for is changes in buying behavior because of the shift to online purchasing, as well as rideshare capabilities or even EV technology. So these will need to be factored into future adjustments in that model. Thank you very much.